Thank you, Tim. Good afternoon, everybody. I will introduce the concept of the Urban Observatory for the people that are not familiar with the UKCRIC strand of work, the partners to it, and then you'll see some examples of work that span three of our observatories. The three initiating ones, Newcastle, University of Sheffield, and ourselves at University of Bristol. And later on, Manchester, Birmingham, and Cranfield University that joined the network of observatories. So the Urban Observatories are the strand of UKCRIC that is there to provide the insights about cities by developing rigorous data sets that relate to urban challenges. So contextualizing, if you like, the research that happens within the large national facilities across the country and bringing that research in relation to what else may happen across the cities. We want to identify challenges in the cities, working with key city stakeholders across the network and the partnership, to take theory back to the city itself, to the urban environments, and see what works and what doesn't. We want to use this network as not only as a research platform, but as a platform to facilitate innovation and engagement with industry, and ultimately to provide the way for others to develop their observatories and become a global example of how to link academia, industry, and key city stakeholders that range from decision makers all the way to individual citizens who may aspire to get involved in common infrastructures like the observatories and have a say in the sense in technology development in the cities. This is effectively done by two things of technology development and deployment on one side, urban sensing networks, curated data and algorithms, and engagement on the other side with key stakeholders in the city who have problems and have agendas and policies that they need to implement. And we can partner up with them and develop insights based on data that have been collected from the city, and they partner with things that are developed in collaboration with other strands of UKCRIC under the umbrella of the whole UKCRIC platform. We do this by individually in each partner city developing the testbeds and the sensing networks that focus on different problems in the cities. Some are common, some are different. You'll see examples of our work across a number of infrastructure problems. Equality, for example, is something shared concern across many cities. And other cities may have very specific issues that wish to explore more by deploying sensing technology, and they're all part of this mix of the network. And we also develop on-site collaboration facilities where we can engage with, as I mentioned, key stakeholders, the city councils, infrastructure asset owners who might come to us and express issues that might be matched up with expertise that we can bring together to work on issues. And as I mentioned, ultimate aspiration is to do this in a way that will lead globally on how to develop this kind of collaboration between the sectors to solve infrastructure challenges that we've been discussing throughout all day. So this is specific in Bristol, our observatory. This is our headquarters. Apparently, I didn't know when we moved in a tower view. This is the tower itself is the second oldest structure in Bristol, which creates more pains than is impressive to say. And also, in the 13th century, it might have had a great view, but now what the picture doesn't show is that we're situated between two large buildings, so the view is not that great. But nonetheless, it's a very suitable headquarters for our observatory. The observatory in Bristol grew out of interest of many collaborating teams in different representative sectors of infrastructure, in water and energy, in transport. When we realized that we can do a lot more together than what people can do in their individual teams. And people can become part of the observatory so long as they bring an interesting problem that they can't solve on their own, and they need the expertise of others. And also they have a key stakeholder in the city, and that they'll bring this kind of real-world ground into that problem. I'll show you an example in a minute. Our testbeds include, for example, monitoring water quality in the Bristol floating harbour, along with the Bristol City Council, monitoring the infrastructure asset that is the iconic bridge of the Clifton Suspension Bridge. We've got intelligent transport people that work with electric bikes and use it to all sorts of effects, measuring people mobility in the city, and also air quality along the trajectories that the bikes use, and many other technologies of that nature that we try to align as meaningful as possibly, and involve as many key organizations in the city that would benefit from this type of engagement. So here's an example of a problem where we got together 2-3 different teams. The Clifton Suspension Bridge Trust has been for many years a good collaborator of ours, and they're part of our collaboratory, as we call our observatory in Bristol, Infrastructure Collaboratory. We wanted to see whether we can develop further insights of their understanding. They wanted to see whether they can understand better the traffic that comes through the bridge, and what kind of alternatives they have to the business as usual from monitoring traffic with CCTV and others. So we've got our structures engineers to hand and our intelligent transport people, and they co-developed a system which looks into the structural excitation and derives signatures of vehicles as they go along, and does traffic characterization. So it complements the insights you can build from either the tolls that exist on one end or the CCTV that is a lot more expensive to process as a data source in that sense. And it's all based on simple structural monitoring equipment that is wirelessly networked together and aggregates the data and applies analytics of transport and are able to characterize traffic. But what was interesting by doing work like that is that unintended positive consequences is that you can get engaged more people when you have that kind of ethos of collaboration and bringing more in. So at the time that this work was sort of producing the first data, if you like, monitoring then traffic characterization based on the structural data, our Data Science Institute had a competition on working with open data, and a couple of artists got in touch with one of our researchers and said, why don't we build a robotic harp that will take input from what you're recording and will produce some music along the way. So that became a good conduit for actually engaging with the public and the media through something that made all that research very tangible and actually producing some music that wasn't very good, by the way, but that's what you get when you play time series that come from, structural monitoring. So it wasn't in any way music to enjoy, but nonetheless the whole venture was to enjoy very much. So our aspiration is to keep working with the Clifton Suspension Bridge Trust as a key partner of ours. They are a representative example of an infrastructure asset owner. They're concerned with infrastructure performance management and how you apply methods, contemporary methods, to problems of performance management. They want to build a digital twin. We were discussing earlier about digital twins, and that's what we will put next as on a list of our work. We'll link the data we collect through the structure to a digital twin, and that, if somebody thinks of it in scale, if we want to do that across the network of our observatories, and so we develop an insight of how do you monitor bridges across sites and across cities. This can be done by DAFNI very, very nicely. You bring all that data into DAFNI, you develop the digital twins that correspond to that infrastructure and have that local insight at the same time that you can develop multiple instances of these infrastructures operating in different cities at the same time. So you can think of many organizations that would have interest in that kind of portfolio management type activity across sites or across cities in themselves. So I think there's a very good case there for us to develop this and then link it to digital twins that our partners will develop in other observatories and over DAFNI ultimately. So this is really the aspiration to keep doing this, develop testbeds in the city of Bristol that we can extract local knowledge and then extrapolate and link up with our partners across the other observatories so that across a number of key expertise in energy systems and mobility and water and infrastructure that we have skilled people in to be able to push the boundaries. And ultimate aspiration, I think, of the entire network is to understand the creation of the soft infrastructure. How do you bring the people together to collaborate on these issues? How do you get the media and the citizen on their own right interested in these spaces? How does technology need to be configured and accessible from a multi-level of stakeholders, from both infrastructure asset owners, people who might be interested to access data about air quality or water quality, because they're citizens and they're concerned about the well-being, and of course researchers who want to push the boundaries of what can be known and what else can we develop as solutions, and so that kind of conduit for brokering those meaningful relationships that will make these kind of projects happen. We want to sort of theorize in the back of it, if you like, how do you do this? The observatories are and UKCRIC as a whole is a platform for doing this, so there's further work to be done on how to establish a formal process to work on that. And on that note, I will pass on to my colleague.
Hello, good afternoon, everyone. My name is Daniel Coca, and I represent the Urban Flows Observatory at Sheffield. I will give you an overview of the observatory, as well as highlight the key research teams that we are pursuing there. Now, our vision for the observatory at Sheffield is to create a platform for understanding and managing urban metabolism. And we want this platform we want to be able to deploy this platform in cities across UK. Now, the idea that cities can be viewed as organisms that process flows of resources, energy to fulfill their functions, and in the process actually generate waste and pollution is not new. Some have traced the concept to Karl Marx, who in 1883, he discussed the exchange of materials and energy between society and the environment. Now, what we're really exciting right now is that for the first time, we believe, observatories provide a realistic basis for translating the urban metabolism theory into practice. Why is that? Because in order to implement this approach in practice, what you need to measure the flows of energy, people, resources, waste, and so on. And this is what we do. And similar to other observatories, we measure air quality, we measure traffic, energy, weather, and we have a range of, for example, pollution sensors, ranging from very expensive to very cheap. And some of these are personal pollution sensors that can be carried and moved around the city. What's distinctive about Sheffield Urban Observatory is the fact that we have two mobile sensing platforms. You can see them on the left-hand side. So one on the far left, that is our Mobius, and it's an environmental sensing platform. And this platform is equipped with the same environmental sensors that we have deployed in the city, fixed locations. It's just that now we can move around, we can calibrate the sensor, we can generate data also at different heights because we have an extensible pole that goes up to 9 meters. Mobius also has sensors that allow us to map radio frequency from mobile mast, telephony mast. The second mobile platform is on the right. There's not a picture there. It's intended to assess thermal efficiency as well as characterize the building materials of the housing stock. And is equipped, at the heart of it is the sensing platform you can see on there, the top, and that is a £400,000 piece of kit. What it has LiDAR, It's got thermal cameras, it's got visual cameras, as well as blind scanners. It's got sensors to measure radiation, solar radiation, as well as GPS and inertia sensors on it. So this data generated from this equipment, now we are developing a processing flow that will take the data, will actually use machine learning, will translate this data into knowledge in an automated fashion. Now, obviously, we are generating huge amount of data. We're talking terabytes of data per day just from the Marvel, the second mobile platform. Clearly, this data needs to be stored, needs to be analyzed, needs to be exploited. And to that end, we are developing an analytics platform that in many ways mimics what DAFNI is doing, but at a smaller scale. And I can show you, this is the current dashboard. But it's not the important aspect of this platform. What is important is that underneath, under the bonnet, we have the same architecture based on microservices that DAFNI is developing. And in collaboration with DAFNI, we are developing standards of interconnections and also agreeing how we divide functionality between and processing between the observatories as well and the central DAFNI facility. What we believe that observatories should be better equipped to do is actually real-time processing of data. And that is something that we're focusing on. Now, clearly, for us, the biggest opportunity in terms of understanding urban metabolism is actually in development of a digital twin of the city. And here are, in our view, the key ingredients of a true digital twin. And these are also the research teams that we are focusing on. You can see their data curation, missing data recovery and fusion. So these are key processing steps that you need to do when raw data comes into observatory. In addition to that, you also need to look at cybersecurity aspects. You need to question whether the sensors that you're producing data are really producing real data, or they are fake sensors, or there's some entity has injected attacks using the sensors to send you wrong information. Now, there is a need for real-time data analytics. Why? Because you need often to get time-critical insights, especially when there is an emergency, where there is an unforeseen event, the city scale. So you need to get your head around what's going on. Now, central to any digital twin clearly is a mathematical model. Now, this model will have to capture the dynamics, but in a spatio-temporal fashion and also multi-scale. It needs to capture the dynamics of processes that happen at different scales. And this is probably the biggest challenge in developing a true digital twin. However, a model is not enough to say you have a digital twin. We had models in engineering for forever, mathematical models. What makes a model a digital twin is actually the ability to update the model in real time, to keep it fresh, to really represent a copy of your system at that moment in time. So for that, you need data assimilation. You need the data to flow in your digital twin, updating the model so that the city evolves, your model evolves at the same time. Obviously, ultimately, a digital twin is there to allow you to do assessment of the urban metabolism as well as design policies. You want to make decisions, you want to make an intervention, whether in short term or long term. This digital twin will provide you with the evidence base. Now, clearly the visible part of the digital twin iceberg are the visualization tools. So we've made great progress together with the help of Mott MacDonald in actually putting together a proof of concept of how to visualize data in the digital twin. And the idea is to leverage technologies to bring the data coming in from your sensors and essentially populate a 3D visualization, which is implemented in an open source game engine, Unity. And so far, we concentrate in a very small area of the campus around the Sheffield University, but at least we have a good idea how this will work, and we are expanding this further. Now, just to give you an idea about the complexity, and this slide is not there for you to read what's on these boxes. It's just to highlight a major challenge we have in the development of digital twin, that of complexity. And the complexity challenge will translate into challenges of defining the functionality, the architecture, as well as standards around this. Now, ultimately, the biggest challenge I believe there is out there is the challenge of resource. We do not have currently sufficient resource to develop a digital twin. With the current resource, I think it will take another 20, 30 years before we actually have in place something that resembles the ideal digital twin. And I think that is where we need to focus on to secure the resource. And if you look at the relationship between DAFNI and the Urban Observatories, what strikes you is that really the observatories provide a vital interface between DAFNI and the real world. So therefore, I think this is where the focus should be in terms of allocated resources when it comes to digital twins of cities in particular. Now, for those of you who are familiar with edge computing or fog computing, there is also an argument about having capability, processing capability at the edges on the observatory side, because that's where you need real-time data processing. You don't want to transfer all that data to DAFNI to do the processing. So this is really all I had to say. Thank you for your attention.
Okay. Thanks, Daniel. I'm just going to spend a few minutes introducing some of the work that's been going on in association with the Newcastle Urban Observatory. I'm not actually, strictly speaking, part of the Newcastle Urban Observatory. I'm part of the Spatial Analytics and Modelling lab at Newcastle, but I'm a DAFNI co-investigator. And just what I wanted to do was actually show you some of the results that's been mentioned earlier today around the hack week that we did with the observatories through a project called Flood Prepared, working with the DAFNI development team, just to give you some idea of what can actually be achieved within about 5 or 6 days of getting a bunch of very bright young things in a room and letting them go and create something around real-time data and analytics using the observatories program. So the Newcastle Urban Observatory currently comprises of about 3,600 deployed sensors around the Newcastle and Gateshead area. It's continuously monitoring or measuring 62 variables, predominantly environmental variables around the city. It's also got access to the full CCTV data feeds of the urban transport system, and that's important, as we'll see in a little while. And it's recording on average about 5 million observations daily. So it's a big sort of infrastructure setup around the observatories program. And the Newcastle sort of observatory concept is thinking around the city as a lab. The idea that you acquire, curate and record all these observations. You then use them within modelling and analytics in order to understand, hopefully better, how the system, the urban system's performing. You synthesize those findings, and that then helps improve your future observations, your deployment of sensors, and then feeds into future improved modelling and analytics. This idea of a continuously evolving circle of evolution and development of the observatories, the modelling and the synthesis and insight. And you do that across all aspects of your system analysis that you want to perform. So looking at, for example, maybe perhaps environmental hazards, looking at the impacts of those hazards, and then what does that actually mean in terms of types of decisions that we're going to make for the population, for the societies that inhabit cities, around policy, practice, design and engagement. So what we did in this sort of hack week that we had with the DAFNI team is, as I said, we basically took about a dozen very talented young researchers. So we took the modelers who've been developing models within certain projects.
we took the Urban Observatory software development team, and we took the DAFNI FTSC software engineering team, and basically locked them away in a room for a week and set them a challenge. And the challenge was around trying to develop the first workflow that could actually try and attempt in real time to basically make predictions of where we expect to see convective rainstorm events occurring over Newcastle, what the effect of those rainstorm events would be in terms of surface water flooding, and then what the effect of those floods would be in terms of the spatial impacts. And this is a project called Flood Prepared that's being run at Newcastle. It's funded actually by NERC over 4 years, and we're halfway through the programme. And this is the first time that we really started to chain together and link together the different models and analytics within Flood Prepared. So, for example, we have the observational data from the observatories, in this case, short-range weather radar data that's being used to parameterize a spatial temporal dynamic rainfall model, which is then used to parameterize our flood surface water flood model, which is then used to trigger our impact analytics and monitoring across Newcastle, which we then try and use to make decisions on where we should avoid, for example, particular parts of the road transport network in real time, or in fact in a nowcasting way, actually ahead of the event actually potentially occurring. So just some examples of the data that we're using from the observatory. In particular, for the rainfall model, we're using 10-minute interval, very high resolution weather radar data. We're lucky enough as part of the UKCRIC Observatories programme to have our own weather radar at Newcastle. It's very high resolution, both spatially and temporally. That's being used to parameterize the rainfall models. Colleagues in maths and statistics at Newcastle are developing the rainfall model, and this comes back to Daniel's point around data assimilation, that as we get new observations and updates in the weather radar data, as we record more measurements around the rainfall gauges, we can actually use that to improve, hopefully, ahead of the event, our prediction of where we're going to see the intense rainfall events over the city. That then allows us to parameterize where we expect to see rainfall within a GPU-accelerated surface water flood model called HIPIMS, which has been developed again by colleagues at Newcastle University. And that can provide us with a time series, again ahead of the actual rainfall event hitting Newcastle, with where we'd expect to see surface water flood inundation and what the actual depth of that surface water flooding is likely to be. And now we're moving on to the point where we're thinking around how do we then trigger our real-time impact analytics. So we're using, for example, deep learning, machine learning algorithms to monitor in real time CCTV traffic flows and traffic counts to try and recognise where we're going to see congestion across the road network, across all 244 CCTV and video traffic cameras that we have in Newcastle. And then we're also using network modelling and microsimulation and agent-based models to try and then simulate how those impacts may propagate across Newcastle as we see the congestion building up in particular locations. So as a result of this, as I said, when we set together the Hack Week, we had a group of modellers, we had a group from FTSC, the software engineers, and we had the Urban Observatory team. And in the process of a week, they basically managed to build what we refer to as the first linear workflow through that sequencing of the taking the observatory data, parameterizing the rainfall model, running the hydrodynamic surface water flood model, and then actually kicking in the impact assessment monitoring and modelling as well. So one of the things that we learned in this process is that the tools you necessarily start with aren't necessarily the ones you end up using at the end of the day. So for example, during the course of the week, we found that we had to use different aspects of the Apache ecosystem, of real-time data streaming and analytics tools, such as Argo and Niffy, which we weren't really thinking we'd be actually using at the start of the week. We intensively use containerization to actually link and chain together all of the models. And we actually successfully managed to actually integrate the impact analytics modelling, or particularly the car counting, from the CCTV. And the result of this process essentially was a final dashboard that was developed by the end of the week, where we could link in for a simulated rainfall event, where we'd expect to see surface water flooding in real time, and then actually then invoke the CCTV data for where we're expecting to see the greatest amount of surface water inundation. So just a little demonstrator tool that we managed to pull together by the end of 5 days. So the key point here is that by working in this way, and hopefully doing more of this type of work in the future across UKCRIC, as has been pointed out by both Theo and Daniel, the DAFNI really provides a glue that allows us to bring together not only the Observatories programme, but actually the National Infrastructure Labs, where there's real test beds around things like sustainable urban drainage, where digital twins are being developed for those, for example. And we can start to think about how DAFNI can be used as that glue for the analytics and the modelling of real-time data within these types of workflows, which are actually quite complex to pull together. The other opportunity with DAFNI is, with this type of approach, is transferability and scalability. We can start to take what we know as best practice or what comes out of projects such as Flood Prepared and actually apply them to other cities. There's no reason as other cities start to become resourced with things like weather radars, a dense network of rainfall gauges and weather stations, that you can't take that capability and then actually apply it maybe to Birmingham or to London to actually use them as a real-time national capability for dealing with these types of events. And it's transferable to actually other types of problems. So been lots of mentions around air quality and also visualisation. And this is some work that Luke Smith, who's in the audience today, has done from the Urban Observatory, where you can actually now visualise in quite a neat way things like air quality measurements across the whole of Newcastle that's being recorded by the Urban Observatory. And again, there's no reason as our skill base and our techniques start to develop that we shouldn't see this as a generic transferable capability to other cities around the UK. And the other opportunity is that the observatories provide us not only with real-time data to parameterise our models, but they also potentially provide us with the information and knowledge to actually validate our models and how our systems are actually responding on the basis of what we're trying to predict. So this is again some work similar to our traffic counting work that we've done, again done by colleagues within the observatories, not within the Flood Prepared project, where they're looking at using machine learning and in particular TensorFlow to count the traffic movements of different types of traffic, so buses and cars, and also looking at how people move and engage around the urban system on the right-hand side, so counting how many people make turns, particularly quite a complex junction. And we can start to use that and bring that to bear into things like calibrating and validating agent-based models, very fine spatial granularity agent-based models about human behaviour within our urban systems. So some conclusions I have kind of tried to pull together with Theo and Daniel, some main points I think that come out of what we've experienced, either myself working with the observatories or the observatories themselves. And the fact is that I think the main observation is that DAFNI offers a unique capability for this melding and bringing together real-time data and capability with the sorts of data sets that we're actually utilising now within the National Infrastructure Database. This melding of real-time and static data with regards to cities and infrastructure. DAFNI probably really does act as this kind of linchpin about transferability and scalability of our analytics and capability around real-time modelling and analytics within the observatories. I can see no reason why we shouldn't be challenging ourselves to roll out national capability on a platform like DAFNI for things like Flood Prepared, looking at the convective rainstorm events, but equally around air quality monitoring and modelling as well. DAFNI is a vital resource around this concept of digital twins. That's been ubiquitously mentioned today throughout the whole of the programme. but it probably provides us with this bottom-up way of innovation-led development of the digital twins, which is embedded within the Gemini's principles. So trying to do it more as a community-driven exercise or piece of work. And finally, I think one of the most important things that came out of our Hack Week with STSC is actually the human aspect of the capability that DAFNI is. DAFNI is now an absolutely unique resource in terms of a set of software engineers who know how to work with infrastructure systems modelers and analytics researchers. And we should actually see that team, the entire team, as being a really important resource to take infrastructure systems research forward into the future. Thank you.